series?
Pull a fourth out.
What did you say?
Pull a fourth out.
Yeah, same thing. What would it be?
1 minus 1 over 4x.
Well, what do I do now? That's my arm. Can you tell me the power series without doing the work? Beautiful. Was that hard? No. It was tricky in that you didn't see it immediately. That's why I said, this is the rule here. It's got to look exactly like this. I can factor things out. That's not even an issue. That's the easiest part of the problem. Oh, so my R would be 1/4 x. Now, can I make this better? Yes. As sort of a general rule, there's nothing wrong with what I wrote, but we would not consider this a finished answer because the x to a power part should always be separate from the coefficient. The an part stands alone, the x to a power stands alone because it has to do with everything when I'm doing analysis later. So I would like to rewrite this. First of all, can I move the 1/4 on the inside? As what?
1 over 4 n plus 1.
And then x to the n. That would be a better answer in general because it would actually be much easier to work with. You know, if I've got to do calculus on this, for example, I'd rather have the x to a power not in a quotient. There's nothing wrong with what I wrote. This is just better. Now, my disclaimer. X has still got to be less than 1 in absolute value? No. 1/4 x has to be less than 1 in absolute value because that's my R. You with me on that? Ah, so therefore, what? 4. And if you look at this, oh, this is definitely a geometric series because I have an exponential on top and on the bottom. If I squish them together as one thing, it's a geometric series, and it'll converge as long as x is smaller than 4 in size because I'm already dividing it by 4 to a power. That was kind of cool, wasn't it? Now, does it get hard? Doesn't have to be hard, but it can become less obvious every time I do something.
-1.
It's not going to work, is it? Oh, unless I do what, Jason?
Factor out -1.
Is that legal? Yes. It's the only way I'm going to do it, but is that hard? No. It's now of the form 1 over 1 minus r. Our goal is to go directly to the power series, no in between. So what's going to go here? We'll do one step at a time. Do you agree with that statement there? Is there anything else needed in there? No, there's no coefficients. So a better version of that would be what? If usually it's the absolute value of x, it's got to be less than 1. No, it's the absolute value of r. So the absolute value of negative x, which would be the same as the absolute value of positive x, wouldn't it? So it's still same criteria. Crazy. Now, just for fun, because that is our primary goal, of course. Just for fun. And this is, again, I'm giving you a glimpse into the future because this is why we study all this crazy stuff. This. Oh, I'm sorry. I left one thing out. My bad. Sorry. I meant to put that in there. Okay. Wait, isn't the integral of the sum of the integrals? So I could make this much easier by breaking it up into an infinite number of integrals. Maybe that wouldn't make it easier. Darn, what the heck would I do? Oh, I don't know. Doesn't have to equal that. But that's just this. Ooh. So there's going to be times when we do calculus of a nasty looking power series and we can get really simple function back because we recognize some details. That's why we love power series in this starting form, because a derivative or an integral of this thing is very, very simple in general. Now, I don't need this today, but isn't that kind of cool? I'm asking you to integrate this infinite sum, and it's going to be this, as long as that is true. Because 1 plus x in absolute value, x can't be -1, can it? That would be a problem. So x has a very limited range of values it could be, but as long as it's between -1 and 1, these things are equal. This is where everything's going eventually. Okay, this is the kind of stuff we're going to be doing. We're going to be taking power series right now and just analyzing them. All I want you to do now is, if I give you a power series, tell me where it converges, tell me where, that's it. Not where it diverges, just where it converges. You're doing a ratio test, fairly simple process. The additional step is, okay, I have to consider the endpoints if it's not geometric. And most of the time it's not geometric. I have to consider the endpoints. But when we've tested the endpoints today, weren't the tests exactly the things we've just been doing the last few weeks? Simple things like simple limit comparison, or it's a harmonic series. A lot of the stuff you don't even really have to do much work for. You're just identifying. Now that I've got that, I'm going to get really good at that, so that when we start using functions as power series, I can then answer bigger questions. That's where this is going over the next several weeks. The coolest stuff is still way in the future of this stuff, but we're just laying the foundation. So everything we did in the first half of this chapter, everything we did, all the different tests we did, we talked about, when things converge versus not. The type of divergence I want to keep emphasizing for a series in general, it converges or it doesn't. I'm just not really that concerned if it diverges to infinity or if it diverges without limit. It just doesn't converge. So now what we're doing with the power series, every power series converges. Every one converges, no matter what. But they don't all converge everywhere. So now let me give you the worst problem. So when I do my ratio test, I'm going to have n plus 1 factorial x to the n plus 1 over n factorial x to the n. Right, so that's n plus 1 times n factorial. This is pretty simple, right? What will I get? Houston, we have a problem. Why? Because I need this to be less than 1. Isn't the n plus 1 term growing without bound? So is that going to be infinity? It will be for almost every real number. Is there a real number out there where this won't be infinite? Is that ever going to be true? Yeah. When? If x is 0, then this quantity is 0 before you take it. It's not 0 times infinity. No. If x is 0, then you just added up the number 0 infinitely many times. Would you say that's pretty boring? Yeah. But does it converge? Yeah, it converges to 0. That's the exception. I can actually have a power series that only converges at one number. All the other one converged over intervals or even the whole number line. I can have a series like this one that grows without bound. It's only going to converge if x is 0. Again, that's not interesting, but it covers every case now. There is no power series that doesn't converge because you can always make the x part 0. Question? Oh, you're stretching. I thought the hand went up. Okay, any question on that one? Again, that's not the one I want you to be concerned about. But it is kind of cool that I will always get some form of convergence. Now, this is not going to be useful to us in any capacity, something like that, because for any real number that's not 0, this is going to diverge. In fact, it's going to diverge probably pretty fast because of that factorial in front, okay? Now, I don't want to do the calculus part of these. That comes a little bit later. But I do want to do the identification part of these guys. There's two ways I can approach this. There are exactly two ways I can approach this.
Multiply by -1.
I like that one better. True or false? What do you think? What do I do with the -1? Does it become negative x here?
Put it outside.
Put it outside. It's just the negative of the power series. It's not -1 to the end. It's not alternating. I didn't make x into negative x. I just factored a -1 out of the sum. That's the easiest way to do this. There's a second way that's not good unless you have other conditions. And I've seen people do this one and they get into trouble. What if I factor an x out of the bottom? First of all, by the way, this is true as long as what? As long as that's true. Agreed? That's still the rule. But if I did this, algebraically that is a true statement. Or is it? Are these equal? Well, isn't what I did legal? Oh boy, we're crossing a line here that we sometimes get in trouble.
That could be
In
zero.
remedial algebra, you solved rational equations. You had quotients of polynomials equal to something, and the only way you could solve it was to multiply both sides by the common denominator, manipulate, factor, and solve. But then you always had to check your solution. And sometimes your solution didn't work. Sometimes you got extraneous solutions. And that was the hardest problem, because that solution literally was a D and E. It was a 0 in the denominator, but you had to get rid of the denominators. There was no other way to solve it. This problem does come up, and it presents a very interesting dilemma, because in certain situations, what I did there was legal, in certain situations. But here's the problem. If I do this one as a power series, then isn't my R 1 over x? So this becomes 1 over x times 1 over x to the n. Is this even a power series? This is not a polynomial. All my x's are on the bottom. But if what I did was legal, then this is an answer. Now we have a different problem. Here's the obvious thing. X has got to be a number between -1 and 1. What's probably the most important number between -1 and 1?
0.
Do you see a problem here?
It can't be.
It can't be 0. Oh, yeah, that really presents a problem. In fact, here's a different problem. What if x is really, really close to 0? Then it's legal. But then these terms are going to grow without bound. But if x is really close to 0 here, then that's just really close to -1. So I ask you, is this legal? It's a yes or no question at this point. No. I'm going to show you why. And this is one of the more important rules You were exposed to this in remedial algebra. You did not dwell on it. It doesn't come up all that often. Okay, so I do this in all my classes. If you were my Calc 1, I may have done this. I have to do this in the higher levels because we run into this problem all the time. When we get to polar coordinates, we're going to run into this problem. All right. X equals 2. Okay. Any questions? No, the hands go up usually at this point. No, I'm just saying X is 2. It's not that interesting. It's like an old Far Side comic that I used to have on my door. It was awesome. The guy has on the screen a picture of a cow. Underneath it says cow, and he says, any questions? And everybody's hand goes up, and it just says, you know, room full of idiots, or something like this. But it's awesome. It's a picture of a cow with the caption cow. Not really any questions. X is 2. Any questions? No, of course not. We know there's something called an addition property of equality and a multiplication property of equality, which says if you add or multiply an equation, both sides by the same non-zero value, you preserve the solution. That's the key. You can change the problem, but that's how you solve all algebra problems. So just for the heck of it, let's multiply both sides by x. Okay? So I get x squared equals 2x. Okay. Now, let me move this to this, because that's the addition property of equality. Yeah, let me factor this. Okay. Piece again, I'll solve this. All right. Okay, that's all pretty exciting. Wait a minute. How did I grow a 0? Is that, what I did was, I actually hypnotized all of you. You've been asleep for hours. I erased the board, rewrote stuff, you know, messed with the clock. Or not. No, I did something absolutely egregious mathematically. I just committed one of the biggest errors that you can possibly commit mathematically. And you don't see it, do you? Let's work backwards. Well, obviously that came from here, duh, and that came from here, and that came from here, and that came from here. So what's my error? What is
0 by x minus 2?
I didn't divide any of it. No.
Multiply both sides by something.
I did something absolutely illegal. What does the multiplication property of equality state? If you have an equation, you can multiply both sides by the same non-zero value. What did I multiply both sides by?
X,
Which can be 0, which means I just introduced an extraneous solution. There's an absolute in mathematics that if it's violated, all hell breaks loose. I mean, dogs sleeping with cats. It's oh my gosh, the worst parts of Armageddon. You can never multiply or divide by something that can potentially equal 0. Ever, in any context, it is the most egregious error that can be performed, because if you do, generally speaking, you may change the complete nature of the problem. I multiplied both sides by x. What if I multiplied both sides by x minus 10? Then we would have had 10 as an extraneous solution. Because we would have created another one because that was not a legal move. Yet, sometimes we have to do this. So in remedial algebra, we've all done this problem. This is baby algebra. Okay? So you said, well, that's x plus 1 over x plus 1, x minus 1, and that's equal to 1 over x minus 1. And everything I said was true and correct, but we have a potential problem here. On the left side, what is the domain? On the left side. All reals, except
0. 1. Wait, 1.
Oh, 0 is fine. Except
1.
-1.
or
Positive or negative.
yeah, we're all on the same page. All reals except for plus or minus 1. What is the domain of this statement?
All reals except positive 1.
But isn't this equal to that one?
Okay.
So shouldn't it have the same domain? A domain in a problem cannot change. There's no algebraic process that can change a domain. If the domain was all reals except plus or minus 1, the domain is still all reals except plus or minus 1. From a graphic standpoint, I have a vertical asymptote at x equals 1. So if I want to know graphically, again, your calc students who will run into things like this more often than not, right? This looks like this graphically. Okay. What does this one look like? Well, didn't I factor and cancel something? So what did I factor and cancel?
X plus 1.
That guy. That was a removable discontinuity, wasn't it? What is the domain of this? The same as the domain of that. So in remedial algebra, do you know what you did after you wrote that?
X doesn't equal 3 to 1.
You wrote the disclaimer. You guys remember doing that in remedial algebra? When you factored and canceled, you said that is equal to this as long as x is not equal to -1, because -1 still is not in the domain. And from a graphic standpoint, it's a removable discontinuity, which we know from Calc 1. Why was that an illegal move? Because I just canceled something that could potentially be 0. Meaning I literally divided by 0. Oh, so as long as I do this, then it's okay. You guys understand? That's what you did in remedial algebra. That's why with limits, there's not so much of an issue, because a limit isn't what's happening at the value, it's only happening on approach. You are never equal to that value. That's why canceling things in a limit is legal, because you're never equal to that value. That's how I can work with things like removable discontinuities. So if we're doing anything where we're canceling something that could potentially be 0, we could run into a problem unless it's outside the domain, which more often than not, that's always an issue. So the power series I did a moment ago, this is not legal, because 0 is in the domain of my original function. 0 is not in the domain of this, which means whatever this gives me is a completely different answer, even though it appeared to be legitimate algebraically. By the way, I don't think any of us wants to deal with something that looks like this, by the way. Now, I do this problem in differential equations, and I'll have a lot of students give me that answer because they saw it somewhere. Why are you doing the complicated one? And then I show them that it's not true. That does not produce the same answer. If I said draw the graph of the two different problems, they won't even look similar. Right? Try to evaluate, they won't look similar. So in the situation where you're factoring and stuff like that, canceling is only a problem if I'm dealing with small finite numbers. If I'm going off to infinity, is canceling usually going to be a problem? Now, you're canceling an x top to bottom, but x is approaching infinity. No, it would be a problem if x was approaching 0 and I canceled x. Or if I canceled x minus 1s and x was equal to 1. That's a problem. But as x grows without bound, that's usually not an issue. Not that part. But in the case here, where I'm choosing the value of x, I've just eliminated something that I can't have. Right? I can't use, I mean, in this case I can't use 0, but in the original I could. In fact, in the original problem, what was it? It was, I lost my x out here. It was 1 over x minus 1?
Yes.
If x is 0, then this is equal to -1. That shouldn't be a problem. But as x gets closer to 0, if I did this, as x gets closer to 0, this one's going to grow without bound. And potentially alternate and all sorts of crazy stuff. Okay? All right, just go ahead and stop that.